Welcome, everyone. This is the John Chappell Natural Philosophy Society Saturday morning science chat. Today is July 1st, 2017. So for today's topic, I was going to go and cover a book by Norman Cook. And this book is, let me share the screen here. This book is called Models of the Atomic Nucleus. So this book has a lot of data on what we know about the atom and some history of what's going on here. So let's take a quick look at the table of contents here. Let's see what would be interesting to zoom in on. And this is the second edition. And in addition to having just a history of the atomic models, he has his own atomic model. He calls it the lattice atomic model. And I mean, some of the key things he has in his book, for example, it says the idea that shells and subcells of the nucleus have a geometrical basis is quite unlike electron clouds, is therefore seen as counterintuitive. For this reason, much of the following text is devoted to showing why, on the contrary, gaseous phase picture of the nucleus should be considered counterintuitive, and how a lattice model can reproduce the exact same sequence and occupancy of nucleons found in the independent particle model on a geometric basis. So definitely he has some different things to say about alternate atomic models. And it looks like he does have an introduction to the low energy nuclear reactions that we were discussing last week. And I think like last week's discussion is maybe perhaps a motivation for thinking that there must be something wrong with atomic models if we're able to do fusion at such a low energy level. So that may be something new with the second edition. So that's the introduction to the second edition. And then they have the preface to the first edition. Let's get to the contents here. So they discuss the basics of the atom, the nucleus, the electrons, shells, and then the nucleon shells. So we have things which apparently happen on the outside, like the radius, the first ionization energy, and things which happen in the nucleus, such as isotopes, binding energies, quadrupole moments. Then there's a brief history of the nuclear theory. We have nuclear models. So they've got several models here. Collective models, cluster models, independent particle models. In part 2, they have long-standing problems. And we've got the mean free path of nucleons, nuclear size and shape. Questions on the nuclear force. Questions on nuclear fission. And they say things about asymmetric fission here. It's because when you split like the uranium atom, it very rarely splits in half, actually. It's more likely to split it into like a 1/4 and a 3/4 fragment than a half. So that's a question. And then they have a section on low energy nuclear reactions. That may be new to the second edition. Then he discusses his own model. which is in this section here. And he has experimental issues based on his lattice model. And then that would be the end of the book. So is there anything there that anyone would want to start with in particular? I'll open it up for any initial comments and questions. Anybody have any particular things of interest?
This is Bill Lucas. When you look at the textbooks and the nuclear physics courses that are taught, there are two nuclear physics models. There's the shell model, which is based on quantum mechanics and the idea of a nuclear potential that holds things together, like the strong interaction. But it can't explain all the data, so we have a second model called the liquid drop model of the nucleus. And you were talking about how when uranium and other heavy elements decay, they don't come apart in half, they come apart in particular sizes. And those sizes correspond roughly to the shell sizes in the shell model of the nucleus, but the shell model of the nucleus cannot explain nuclear decay, but the liquid drop model can. So we've got two models that are used, and the question is, why do we have two models? Normally, you have one model. And
yeah, those models are mutually exclusive. You can't do both at the same time.
that's right. So they're incompatible with one another in some sense, and so that has been a problem for a long time. And the other thing that has made a problem in physics is that NIST has initiated uh, an attempt to fix some of these problems, like the two models of the nucleus, and so they gave out grants to measure the nuclear isotope masses and all their properties, the way they decay and that sort of thing, to 8 significant figures. And that is way better than the quality of the data and the accuracy of the data that what existed at the time the nuclear shell model was created in the liquid drop model. So what has happened with that is that it appears that uh, there's no more evidence anymore for the strong interaction force in the nucleus and the weak interaction force in the nucleus. And so that is very disconcerting because that means you have to throw out quite a lot of stuff. And the scientific community is unwilling to do that. So they don't emphasize that. But the first person who pointed that out was named Carl Johnson. He was associated with the Fermi National Accelerator Lab and the University of Chicago. And I don't think he's in the physics community anymore because of being blackballed for having revealed that information. But he's not a member of our group either.
Mm-hmm. Yeah, I was just looking through the book for references to shell model and liquid drop model, and certainly he mentions that quite a bit in this particular book here. So I was wondering if he summarized what those two models involved. I mean, as I understand it, so the shell model says that the nucleus is built up out of different layers. So like this picture on page 40 is showing what the various shells would be inside the in the nucleus. Now the liquid drop model presumes a more amorphous kind of structure, just like a water droplet where the protons and neutrons are more or less randomly distributed through the nucleus. I wonder what he has to say about, say, Rutherford. See if he mentions.
I'd like to point out that there are other models as well, the liquid drop and the shell model. There are other lattice models in nuclear science. What's particularly interesting about Cook's model is he's using a face-centered cubic lattice. Other models use um, a just a cubic lattice, not a face-centered cubic lattice. And this sort of thing goes back quite a ways. I think Linus Pauling had a spheron model of the nucleus, like a closest packing of the nucleus model, and there's others. This has been around, kind of thing has been around for a long time. But what I found really interesting when I was first introduced to this years and years ago was that in Cook's model, he's able to take the quantum numbers and assign XYZ coordinates to each, quantum, not quantum number, but group of quantum numbers. So he can position a proton or a neutron according to that proton and neutron's quantum numbers, complete set of quantum numbers, and it forms an FCC lattice. That's what I find very interesting. Of course, FCC lattice, I think, is the lattice structure of minimum energy close packing of spheres.
Yeah, let's see here. Where's this picture of his model here? I think he's got his pictures of his models.
By the way, in the group
like
chat, I just posted the web address to Cook's website where he's offering his visualization software. I played with that software years ago. I find it very interesting because he models both liquid drop and shell, and as well as his FCC model. And you can click from one mode to another and kind of visually see the difference between these different models. Very nice.
Yep.
These pictures that you're showing on that page is from his software, I think.
So it looks like his lattice model places the nucleons in basically a octahedral type structure, it looks like, as you get larger and larger.
One of the tests that can be used to see how accurate these models are is to predict the nuclear spin of the nuclear isotopes. To give you an example, the shell model misses 1,300 nuclear isotope spins. It can't predict them, or 1,300. It does the other 2,000 and some, but that's a big problem. And and the other thing is you've got to be able to explain the islands of nuclear stability, be able to predict them, and you also got to be able to predict the decay modes for each of the nuclear isotopes. They may be a nuclear isotope may have that's radioactive may have 2 or 3 or 5 different modes of decay, and so that's something you have to be able to predict. The decay is handled by the liquid drop model more than the nuclear shell model. Nuclear shell model has the like islands of nuclear stability and the spin of the nucleus and the binding energy, the mass of the nucleus. That's another thing. You got to be able to predict the mass of these various nuclei.
So I'm looking at Norman Cook's website here. So looks like he's got a lot of things here, and I guess he is in. He's belongs to the Okasaka, Japan University. So he's still active. So I was wondering, you can probably ask him questions if you want.
So, Bill, may I ask you something, or maybe to explain to others, at least to me, regarding those magic numbers? What are those numbers, and how this approach and your approach relates to covering those sets of so-called magic numbers?
Well, there's certain nuclei that are stable, and there's some with the same atomic mass that are unstable. And so one wants to know, what the origin of the stability. And the shell model, they're able to predict a certain number of nuclear shells, but there are other shells they miss. And so, but we have the data, so we know they exist. So that's a problem even for the nuclear shell model. But we started out with the plum pudding model of the nucleus, and then we went to shell models to kind of mimic what we were doing for the outer atomic electrons. And but the outer atomic electron models now, which is your Bohr model, your Schrodinger model, and your Dirac model, they now are supposedly being falsified because they cannot predict half of the nuclear states, not nuclear states, atomic states of atoms. And and that is based on the extreme ultraviolet data that NASA has taken in space. It turns out that you can perform experiments in space that you cannot perform on the Earth, because in space you don't have to enclose your sample to do spectroscopy in a container, and like a glass bulb or something like that if you have a gas. And so, for instance, if you want to measure the emission spectra of hydrogen or helium, you cannot measure it in the extreme ultraviolet on the Earth. But in space, where you can just have the entire apparatus exposed with no container, you can measure it. And so that data has shown that all known atomic models only predict, at best, half of the emission lines for the atom. As far as I know, that type of data has not been taken on nuclei. That would be interesting to find out if NASA is going to do any nuclear experiments out of space, because you can measure things out there you cannot measure on the Earth.
Now, there's a section on magic numbers in this book here. He mentions it several times. Let's see, where is the... looking at this mentions a lot of things probably worth taking a look at. Let's just take a look at some of the data that
I did
got
go.
here.
I did search, but there was no place where that term would be explained, somehow. Oh.
So here's a classic plot.
There is some table that they show the available data and missing data.
So, well, the magic numbers have to do with basically nuclear stability. So this is
nuclear. At least get the pronunciation right. Nuclear.
Nuclear.
Not nuclear. Not nuclear. Nuclear. Nuclear, not nuclear. Please.
Well, sorry. So I'm afraid I'm gonna have to pronounce it however I know it. If that offends you, then it's like
It's important. You mess other people up. You make the whole society look bad by saying nuclear. It's an easy fix.
Like
Really?
nucleus, nucleus and nuclear,
Nuclear.
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 Nuclear. Nuclear. It's spelled Nuclear, not Nuculu something. It's Nuclear. Nuclear. Really, this is not trivial. It makes the society look bad when you sound like that.
Again,
So I'm sorry it bothers you that much, but
now
I'm going to
clear.
just speak sometimes. I'm going to speak up sometimes, and if you're going to kick me out of society, go ahead and kick me out. But that's the way it is. Nuclear.
All right. Well, I'll try not to say that word because I know
You're
I'm going to say
typing
it wrong.
like clear, right? Like clear, like nuclear, nuclear, like clear, right?
That's
Now
right.
it is clear, nuclear.
That's right.
It's like
That's right.
tomato, tomato,
No,
call
no,
the whole thing off.
no, no, no,
Okay.
no.
Well, let's get back to actually looking at, let's
I'll let you go. Go ahead.
let's go look. So that is the list, the table of isotopes. Let's see, where was I?
These two tables, these two graphs might be relevant.
So that's the list of radionucleotides. So the dark ones are the ones which are stable. The gray ones are the ones which are not stable. So as we go up, we can see that, and this particular chart looks a lot better if it's actually zoomed in. But this generally shows the available atomic atoms you can have and their isotopes. So not every single isotope is possible. So you can't take like carbon and stick like 500 neutrons on it. It won't take that many neutrons. It'll only take a certain number of neutrons before it won't make an atom at all. And
Also,
conversely,
this chart is incomplete in that it doesn't show the islands of nuclear stability. In other words, you're seeing one continuous kind of like run of nuclear isotopes, but then there's a space where there are none, and then farther out there are islands of stability, and there's about 10 of those. And they're not
let's see
shown.
whether, because that chart really doesn't show things too well. That's just a general map
There's
of
a graph.
everything.
Take a look at that graph. That part of it is visible here now.
So let's see. This is the so this is like showing some of the magic numbers, and let's see. This is known isotope.
Okay. Here we have here kind of right the known isotopes and the stable and metastable and so on. So now these numbers here, what they designate here? Those numbers of protons, numbers of neutrons, sum of protons and neutrons.
I'm trying to figure out here. I think that's the chart says neutrons, so it's basically the number of neutrons.
What
this
is
is
interesting
probably
is the latest NIST data shows there is no such thing as a neutron in the nucleus. There's no nuclear isotope that has neutrons. And you can, but that's newer than this book. Actually, the book came out, the second version came out in 2010, but that was coming out about 2006. And
What does it mean that there are no neutrons in the nucleus?
That's right. And there's no nucleus that decays and produces neutrons when it decays.
Okay.
But we can make experiments and we can make neutrons with accelerators and things like that, but they don't seem to exist in nuclear isotopes.
So here's another chart showing, I guess, protons. So probably a higher peak is more stable. So the thing about the magic numbers is that it's kind of a rule of thumb, and that you could point out, because I looked at the magic numbers personally, and it's like they're not magic by a whole lot. You'll see that in this kind of data, there'll be some peaks, but there'll be some peaks at different places. Like they've got 78 and 84 and 94 and 36, and all of those could be considered kind of magic, but it's not something that really jumps out at you. So let's see what other references they have. What other charts they have? Let's see.
Can I ask for the binding energy chart? Because I've done some research in my lab that relates to it. I don't know where it is on this book, but there's
sure
usually there's usually a chart of binding energy, and it shows how much it takes to split apart each isotope. Specifically, helium is the one I worked with. I was able to take americium from a smoke detector, put it in my vacuum chamber, and have it split on a gold foil. Have the alpha ray. It emits an alpha ray. That's it. That's the one. What does it take? What would it take to split helium into, to split it like a wave? See, I've been looking at the wave particle duality. All of this, neutrons diffract, protons diffract, atoms diffract. What does it mean for it to act like a wave? And then you do all these models of a particle. What is going on there? So I put many years of research into that, and actually succeeded in splitting the atom like a wave. And so this is why I want to point out helium, because that's what I did it with. The americium, it's a much heavier isotope, and it puts out helium, which is, it puts it out in the form of an alpha ray, which is the helium nuclei. And then I split it at a gold foil, very similarly to the way Rutherford did his experiment to show the atomic nucleus model. So it should go one way or another at the gold foil. It should bounce off or go through. That's the alpha ray. But I found I was able to do a split of the alpha ray to make it go two directions at once in coincidence, more often than accidental chance. Does anybody understand what I'm talking about?
So, were you getting two alpha particles out from one? Or
I did it. I'm the one who split the alpha like a wave. No one else has done this. I did it about 10 years ago, and I've been telling everybody ever since. But so it's not well. But it's on my website, and you can see it and everything. It's in my literature. I'll be talking about it when I come over.
Who is talking, please? Is it Jim Marsan or
Eric Ryder? Eric Ryder.
Okay.
Well, let's take a look at this chart here. So the significance of this chart is that it has listed all the elements basically in orders of 4 for protons. I could go from 4, 8, 12, 16, 20, 24, 28. So these are all incrementing by 4 protons. And
it's a beautiful thing.
So at least 7, the first of 4 or 5 atoms they have listed there, there seems to be a peak for like carbon, beryllium, helium. oxygen have a pretty
Right.
clear peak, meaning
Right. I
that
went to the
there's something about this number 4, which is very significant.
That's right. That's right. I went to the first peak, number 4, helium, and it
But
says 7 there, 7 MeV. So that's what's important. So the alpha ray, when it comes out of americium, it comes out at 5.5 MeV. So it does not have enough kinetic energy to split by this chart. This chart, it was done by collision experiments, is how they figure this out. So what I want to know is, well, look, did I make any mistake? I've been looking at this for many years and talking to people. I haven't found any mistake in it. But I would like to bring it up that, look, there's something about splitting as a wave to get through to a realistic model as to what's going on here, because it's not always particles. There's something very fundamental about how this all splits up into waves.
Okay, so your indication is actually that you get two waves, two kind of identical wave phenomena out of one alpha particle, right?
Yes, that's the profound thing. Now,
Okay. Then I think I could contribute to hear something based on the electrodynamic mechanisms involved. I mean, kind of one proton is one toroidal vortex, and neutron is actually the same form, but kind of covered up by kind of ether, layer, so that its electrical features have been kind of suppressed. So in alpha particle, you have two protons and two neutrons, and then if they split into two halves, then maybe depending whether the neutron gets activated into in part of its electrical features. Anyway, I mean there could be a wave, mechanism that actually that movement on the toroidal vortex actually induce the complementary structures in the ether, so that manifests as wave.
All right. Let me explain a few
Yeah.
details. When you split the alpha as a wave, usually it goes to 2 half-height pulses. So the pulse height is an indication of the kinetic energy, and so that's it makes sense for it to go into 2 halves, because you would think, oh well, maybe I'm splitting it into 2 deuterons. Usually it did that, but I did not have enough kinetic energy by that chart to split it into 2 deuterons. There's something else going on.
Okay. Maybe the concept of the concept of strong force is actually kind of might be misleading. Actually, in what is involved is actually electromagnetic of attraction and repulsion. The difference is only in the closeness of the structures and so on. But essentially, it is kind of electromagnetic. I mean, the notion of strong force is a little bit kind of artificial. So you should not be hindered by the notion of that strong strong force that it would not be able to be released. I mean, for those two structures, two halves to be released. It is more like electromagnetic, right? I mean, this will be my contribution.
I was able to defy the strong force, but let me get to the next step. Some of the splits actually were full height pulses, to where you say it was 2 for 1. So you can tell that it emits one at a time by doing a true coincidence test, by rearranging the detectors. And everybody, they know that the alpha ray emits only one at a time from that decay. So I was able to see 2 full height pulses at around 6 times greater than accidental chance. So that's saying another thing, that's another important message. That's indicating that helium is sort of in everything, which kind of makes sense. But it's loading up. It substantiates this accumulation hypothesis that I've been showing works. It works with, I've done it with gamma rays and alpha rays to show the loading theory.
So could you share some paper or some article or something?
Well, maybe you can put in the chat a link to your stuff, Eric, and people can take a look at that.
I don't know how to put it in the chat, but it's all on my website, and it's already on your website, on the Chapel Natural Philosophy website of my abstract that I'm going to be delivering in a few weeks. It's already there.
Are you going to the conference?
Yes, I'll see you at the conference.
Yep, I'll be at the conference. Well, let's get back to the book.
Good.
And your family name is Ryder, R-Y-D-E-R, right?
R-E-I-T-E-R. So it's Eric Ryder, R-E-I-T-E-R, and so I'm on the I have the abstract posted on the CNPS website. And it's easy to find my work.
So getting back to the book, so this is one of the charts that they show about why we think electron orbitals exist, and they're showing the various shells like K, L, M, N, O, P, and Q, and these lines coming up from the center there basically indicate the transitions. So like you can go from 3 to 1 or anywhere in between, and you get basically the spectra from that. And then to the left, they have like for example, a theoretical example of what the electron cloud could potentially look like. I've always criticized these things looking like balloon animals together, and I can't really possibly see how they could ever maintain such a structure, but there it is. There's an example of what they think the electron cloud looks like.
Yeah, actually, yeah. I could put to some relation to the heterodynamic structures that come out in the Tsiukovsky's analysis.
And this is a picture of the theoretical nuclear texture. So as you go out from the center, you see that its density decreases to 0 as you basically go from about 2 centimeters to 4. So that's an experimental piece of data. And here are some other pictures of what these orbitals look like theoretically. Like I said, they kind of look like balloon animals twisted together, with somehow the electrons maintaining these states. Although we don't know of anything that would cause them to do that, and certainly the Coulomb's law would not allow them to do that. But yet we have those pictures.
Those are theory pictures.
Yes, those are theory pictures.
Right.
I personally think they look completely ridiculous. That would be my opinion. Okay, so now this is the
electron is not a particle. the electron has to be smeared out in some way. It's some kind of standing wave.
Actually, I mean, the electron, okay, straight away, actually, this structure is kind of toroidal vortex kind of structure. I mean,
Right.
the
Vortex.
consisted of movements that actually kind of topologically make that shape. And in the atom, it is more kind of how say, some layers and some flows again. So as a free, it looks similar to photon, like half a photon, or
Well,
so. I mean,
that's all the
if you would
questions.
be, if you would be at some point, if you would allow me to put some pages on the screen, then I may just provide some idea about. I mean, what is the
I
structure of
mean,
what
well,
could be the structure of electrons? I mean, those clouds kind of. But again, all the time, it's kind of flow. Yeah. But flow of particular shapes, and then there could be some similarity seen between what this book is present, different models, and the heterodynamical model.
okay, well, going on the data they're presenting here.
Yeah.
So this is like the number of electrons in each of these shells. They're up to 8 shells. And they're showing the number of electrons in each shell. And they go up by particular numbers. So first shell has 2, the second shell has 6, the next one has 10, the next one has 14, and the next one has 18. So that's an interesting piece of information. It's like, why those numbers? I mean, 2, 6, 10, 14, 18 does not seem to be following any real particular sequence, except there's a very strong, like, 4. They increase by like 4 each time. So that would be a pretty strong number. And once again, the number 4 seems to be fairly significant in atomic physics. So why is that? Why is it the number 4 is so important? So that's another piece of data. And let's see here. This is the radius. So we can see that this is basically the size of the atom. And I believe the minimum we see there, those are the Nobel elements.
I always have to look to see how they do these things. Does anybody have any idea how that was experimentally figured out?
The radius?
Here we're looking at a chart of something. Well, how did they do that?
Well, I think it'd be easy to figure out the radius if you had a solid piece of whatever element you're looking at. But if you have like a gas, yeah, it'd be kind of hard to tell, what would be a comparable diameter for an atom.
You can get this data that's being plotted off of the NIST, National Institute of Standards and Technology website. And for each piece of data that's on the chart, they give you a reference to the paper where it's published, and it describes the experiment.
Obviously, it's a bunch of data points. It was done from experiment. There's an important experiment that relates to this chart. And when I see a chart like this, the first thing I need to hear is how do they do it? There's going to be some straightforward explanation of what kind of experiment that was done for the whole chart.
Well, that's a good question. I'm sure probably if you did a Google search on it, you would probably find out. But what's significant here is that each of these peaks is like the element right past the Nobel, the noble gases. So the size of the atom basically minimizes as you say go to neon, but as soon as you go one more to like sodium, then it gets just suddenly much bigger, and then it starts getting smaller and smaller and smaller and smaller until you hit the Nobel gas, and then it gets much, much bigger. So it would seem that the noble gases have the most compact expression but when you get like you add one electron to it, it's probably not very well bound, so it has a long ranging effect and probably increases the size of the. It's just like they seem to be loosely bound, I would say, until you get back to the Nobel element where it becomes its most compact again. So that is an interesting bit of data, that it changes sizes like that, and it's pretty consistent.
There's undoubtedly some kind of scattering experiment, but
Probably.
there are assumptions that go on all these experiments. Then to discuss a chart like this, it's the first thing to find what are the assumptions behind it's probably right. I would, after I read it and see it, I wouldn't argue too much with it. But to discuss it really requires something about what the experiment was that brought these things up. I always try to find that. So part of the problem is the books that deliver these things, they don't put that right up front. They make it seem as if it was delivered by God, and it's disturbing to me. So it's all beautiful stuff. I love it, and I don't know the answers to all this stuff. So I just want to point out that going to the experiment and seeing the assumptions is really the first step behind to interpret a graph.
Yep. So now they have the ionic radius, which basically looks the same as the covalent radius. I'm thinking that they say covalent because that's the distance that you measure when the atoms are actually bonded together by covalent bonds. And I'm presuming ionic radius is like, what's its free radius? But pretty much it looks the same. That your Nobel elements are at a minimum in each of these charts. Let's see what other information. So you have ionization energy here. So here we also see a very, very strong periodicity here. That the highest energy ionization energies are found at the closed shells of 2, 10, 18, 36, 54, and 86 electrons. So the ionization energy is the amount of energy it takes to remove a particular electron from a large enough atom. So we can see like it like goes like the maximum, the hardest electrons to remove look like the ones from like a Nobel element. But once you get to the next one past, that electron is relatively loose. So you see this big drop. That's again indicating our Nobel elements are special. And once again, the Nobel elements are all basically divisible by 4. So once again, that number 4 seems very significant. That anything made out of, and this is also called, I'm not sure if he mentions it, but this is like the alpha model, where basically the idea there is that all atoms are basically made out of clusters of helium, as Eric indicated, and that those are stable because of that there is this incredible stability of helium within atoms. And if you have an atom made entirely of helium nucleuses, which would be all the Nobel elements, that those would be the most stable and non-reactive atoms. And we have electronegativity. So what is electronegativity? That is, I think that's its ability to attract another atom to form a molecule, I think. I'm not 100% sure about that. But once again, we have basically that same kind of pattern going on. That as we stretch, every single time you hit a Nobel element, it like causes a massive change in the data. What else do we have here? We have boiling points and melting points. Okay, so this is a little bit more all across the chart here. I don't see any really, really big pattern in the boiling point. And the melting points, we can see, of course, the Nobel elements want to be gases, so they melt at very, 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 very low temperatures. So we can see more of a pattern here in the melting point chart here. Heat of vaporization. So once again, we can see a pretty strong pattern based around the Nobel elements. It's the inert gases all anchor the data. And now this is the isotopes we were looking at before. And this is a chart of the abundance of elements in our solar system. So you'll see that there's a lot of helium and carbon and oxygen seem to be very abundant. One unusual peak you'll see here says Fe for iron. That there's a gigantic peak over here that really shouldn't belong. It should actually just go smoothly, but there's this gigantic peak of iron here, which is unusual. So you kind of have to count, why is it there's so much iron in the Earth, right? And last week I mentioned that when I was fusing carbon and oxygen, that we can detect iron in that reaction. And part of that may be because iron is favored to be formed, as is shown in the abundance of elements in the solar system. That there is an unusually high amount of iron. And so you kind of have to explain, why is it there's so much iron compared to everything else. And also during the experiments, other people have, like these fusion experiments, other people have measured the other elements. I mean, I only detected iron because that was easy, but the fusion experiments where you spark together the carbon and oxygen, the carbon rods, actually produces a wide range of elements, generally speaking, in the same abundance as found on the Earth. Did you have a comment, Eric?
Yeah, the fission, when they decay, it all goes towards iron. From that direction, the higher elements will do fission. Fusion, when they're unstable, they go towards iron. There is a beautiful stability that happens at iron, where from both sides, fission and fusion, it aims towards iron.
Yep. Yeah, there's another graph around. I'm sure they have it, which shows that iron is basically the peak of the energy curve or something. Let's see if we can find that one. So there's something special about iron. And iron is also one of the few ferromagnetic elements, along with nickel. So all of your magnetic materials are in that peak. So I don't know if there's a relationship there, but we're just looking at the data here. So I'm not exactly sure what this chart is showing about nuclear binding energies. I think they're trying to do something about the shell structure. I am not quite sure what that is about. Then we have something, a nuclear quadrupole moment, which seems to be, and this is for odd nucleons. So odd nucleons all have this nuclear moment. I think now basically, do I have an equivalent chart for evens? I don't think they do, because basically a lot of even nuclei don't have that moment.
Franklin, could you put those pages to the full screen? Maybe just to eliminate, to increase the area, maybe.
we can zoom in a little bit here.
But you know, if you would remove those fields to the left and to the right.
Well, I don't think that would help, but I'll see what happens. So all that does is,
Oh, yeah, just move. Yeah, shift the.
how do I get rid of this one? I think I could scoot that one to the side there. Okay, so now where was I? We've got all this interesting data to look at. So if you have a model, the idea is try and come up with a model that explains all this stuff.
Guys, if you will be interested to support the translation of the Tsiolkovsky's aerodynamics, then I think virtually everything would be possible to explain. I mean, it will be really kind of interesting and I'll say. I mean, it, I could show you some of parts, you know, just to get an idea. I mean, it's really amazing how everything can be.
So, but there's a lot of data that's available. So, I mean, a lot of these things, I'm not quite sure what they are. You have neutron separation energies, proton separation energies, plots of nuclear charge radius. So I believe that is the section on data that he has in this book here. And we've already covered the shell model. So he has a brief history of nuclear theory here, which he says was started by Rutherford.
You can increase. Can you zoom in the page maybe?
Well, if we zoom in, then we won't be able to see
Okay.
much
No.
more there.
One more. Yeah.
Let's see here. So this is the brief history. And he's mentioning the special stability of 4N nuclei, which is the alpha particle.
Can I show you? Can I show you the structure of the alpha particle to see what the stability would mean?
Well, if you have a picture of it, you can put it in the chat, and then I can click on it.
I have book here. I mean, I would how to say walk you over a couple of pages, you know, just to get an idea.
You mean just show it in the video?
The book is in Russian, otherwise, no.
Well, if you would like to, you know, we can actually have a meeting on that paper if you'd like, and you can lead it on that. But right now we're taking a look at what's in Norman Cook's book here. So a lot of data. So here's a list of all of the nuclear models he's got here. And there's quite a few. Independent particle nuclear model, strong interaction model, liquid drop model, Fermi gas model, potential well model, compound nucleus model, optical model, alpha particle model, shell model, single particle shell model, many-particle shell model, JJ coupling, unified model, collective model. There are a lot of models available. So, and I don't think that there's, you know, even now in mainstream, a real consensus about which one of these are right. It's like the most popular ones that we had mentioned was the shell and liquid drop. And the main problem with that is that each of these models can only explain some of the data. And it doesn't seem like there's a tremendous amount of consensus about which one is correct. So this is an opportunity to advance science if you can figure out a model which encompasses all this data, but is only a single model and not multiple models. So this is an area I would say we are still in the dark.
I bet you the Tsiolkovsky's aerodynamics at least will be best covering everything here. Possibly everything. Exactly, really everything. No? So,
well, then how do you explain the asymmetric fission, for example.
Okay. Can you explain when you look at how proton and neutron fit together and what neutron is and so on, the neutrons, as I said, is proton covered by a layer that suppress its electrical features. I mean, the mass, everything can be explained. I mean, this guy have put many things there. If something is missing, then I really believe that based on that insights on that, how I say, model or mechanism, it's really kind of substantial. It's nothing like like abstract, like quantum mechanics or that model which is there. It's just fluid dynamics, gas dynamics, mechanics dynamics.
Well, like I said, if you would like to present what he's got there, we'd be happy to listen.
Maybe I maybe can walk you through a couple of pages and just to get an idea, and maybe to interest of you somehow go over it. I mean, I'm really little by little just using little time to translate certain parts. I have been contributing them to the group. When we are talking about photons and about electromagnetic propagation and the structure of waves and things like that. Now this topic is kind of important. Always is kind of at stake today. And
well, I think next week, we will go over specific other people's models. So
okay.
if you want to present, why your model is best, I think that would probably be the opportunity to do that.
Okay, then. So.
But today we're mostly concentrating on just looking at what's in this book.
Pages of the Tchaikovsky book and walk you through it, kind of, and explain particular parts, structures, mechanisms, and so on. I mean,
yeah. So if you could, put them in like a document, like a PDF or something like that, then we can show them in the meeting. So if you can make it something like that, that would be great.
Yeah,
but,
to extract.
Can I add my pictures also about my experiments on splitting the alpha?
Yeah, that would be great, really.
Yeah, you can. I mean, so like I said, next week we will probably be discussing the other theories. Like, I have my own theory. Bill has his own theory. Slobodan has his own theory.
It's not mine. Okay, it's not my theory. It's kind of theory of. It's not kind of how I say.
Yes.
Yeah,
Zhukovsky's theory.
Yeah.
I'm the one here who has experiments. Does anybody else have any experiments? Has anybody else here done anything? Well, I don't think so.
Okay. How about we go this way? Take this experiment that Eric has, and then try to see how different theories approaches would explain that. Okay.
Yeah, that is one thing. That's a good thing we can do with experimental data, because like what we're presenting today is all this experimental data, and try to fit it. Now, here's a list in this book about the different models. Now, it seems like all these different models can explain some part of the puzzle. Like the shell model can explain the magic nuclei. Some can explain the angular momentum. Some of them can explain constant nuclear density. Some of them can explain why alpha particles come out, and various other things. So, but what we're looking for is one model that explains all of these things. So this is the history of the evolution of nuclear models here. So one half is have strong nuclear force models, where we have the liquid drop model. We have central potential well models, which I guess don't have the strong force. So I'm not quite sure. I thought all of them.
These are shell.
Force.
These are shell model. The general potential well models is a shell model.
Yeah, the shell models versus the strong nuclear force we seem to have are liquid drop models here. And where does he put his lattice model in this thing?
It's on the right, near the bottom.
Oh, near the bottom, lattice model. Of course, I don't think they have my model here, which says that there basically is no tiny nucleus and everything is put together by the electrostatic force. I think all of these still accept the idea, the Rutherford model, that the nucleus is separate. But I think, that's in contrast with, like, say, mine and Build model, where we believe that the electrons, the nucleus and the electrons are basically mixed in together and that there is no strong force present. So I don't think he's covering that particular kind, but that isn't a list of all the known elements here.
One thing I'd like to point out is that we have more than one type of atom that uses, say, electrons. We have atoms that use negative pions. We have atoms that use negative kaons. We have all kinds of atoms, and they all have their set of data. And one theory should explain all, not just the electron atom.
Why should we be considering the particles that are results of breaking the dynamically stable or relatively stable structures? Why should we bother about that at all?
Because they each will explore different aspects of the nucleus.
No, there is just one aspect. I mean, my point is that the structures are stable. We are talking about proton, neutron, electrons, kind of atom, right? And then putting it into discussions, as has been, I mean, the mainstream and here nowadays as well, the fragments of those structures or hypothetical particles, confirmed or not, is for me kind of superfluous and unnecessary, obsolete, totally misleading, and kind of something really worth abandoning totally.
Well, the current models, like the Dirac model of the atom, which is the politically correct model today, cannot explain the other types of atoms, like muonic atoms, pionic atoms, kaonic atoms. Can't explain that. And we have made measurements on almost all the nuclear isotopes forming atoms out of these particles. And so uh, uh, there needs to be a more general approach to the atom that can explain all of those data. That's what I am doing in my work. So if you can explain just the electronic atom, well, you're one fourth of the way there. You've got three more kinds: muonic, kaonic, pionic atoms.
For me, I mean, it's only important to cover and address and consider the one, the only one atom. What does it mean now? I mean, considering some modifications of intrinsically flown concept or structure.
Well, what is a pionic atom? I've never heard of such a thing. What do you mean by a pionic atom?
Well, you make pions, and you then let the pion beam stop inside of a material, let's say like carbon. You have a carbon block, and what happens is the negative pion kicks an electron out until it has kicked all the electrons out of an atom. And every time it does that, you get an emission spectral line, you get all kinds of information out. And the pions, for instance, are much heavier than the electron. So at one point, they are inside of the edge of the nucleus. So they give you information about the structure of the nucleus. And so you get a picture of the nucleus from that. And you do the same thing with muons and with kaons. And each one of those has different information that it reveals about the nucleus and also about the structure of the particles outside of the nucleus. So you have a shells of pions, you have shells of kaons, shells of
But
muons.
okay, those are shells not exactly consisted of those pions, whatever, but some information measurements that is produced by using those particles to probe to how to say inspect those structures, right?
No, you're making atoms out of those, and the
Well, let's
atoms
just,
exist for
you're
a
just
certain period of time.
substituting the electron in the atom. So if you had hydrogen, instead of having a regular electron, you'd replace it with a pion.
Right, or a
And then
muon
that,
or a kaon.
yeah, muon or kaon, you just replace the electron because they're all just -1 electrical charge. The only difference between the electron and the pion, the muons, though they decay, fairly rapidly, but they can stick around long enough that you can measure like the spectra, and the spectra will be different for a hydrogen atom that has a pion around it, or a muon or a kaon around it. So that tells you something about the shells.
It's charged with a higher mass. Is that what's going on?
Yeah, the kaon and pions are electrons with higher mass.
It's hard enough to understand the electron. I mean, yeah, it could be interesting to get a theory with all of those other ons, but we don't know how to do it just with the electron, do we?
Well, some of us claim we have done it, so we'll see.
Yeah, we'll see.
Model with the electron with charge alone, normal charge, a consistent model. Look, you have a problem just with wave particle duality. How do you do that? Just go back to something really. My point is that you're skipping over something more fundamental in this wave particle thing that I've been working on.
Yeah, we're having a hard time hearing you, Eric. You're kind of cutting out on us. But,
I'm sorry. I have a boom microphone. I was doing the best I could.
Okay. So getting back to the book, so he's visualized what some of these various models would look like. So on figure A, that would be the shell model, where basically all the particles are attracted to or associated with a central core. So everything is pointing to the middle there. And pretty much each of the individual particles are ignoring each other because everything is attracted to the middle. And then B, we have the liquid drop model, where every particle is basically associated with just its neighbor. And then C is a semi-solid cluster model. I think that's more like an alpha model, where the important thing is those clusters of 4. And then finally, D, we have the quark model, where the constituent quarks are just flying around in a gigantic cloud. Of course, none of these models really kind of lend themselves to the fact that each of these atoms forms very specific geometric structures. Like if you crystallize something, like say a gold atom, if you let it do a natural crystallization, it will form like an octahedral shape. And of course, none of these really have any specific geometric shape, especially the liquid drop model. That's just going to be some amorphous blob that you would find difficult to think that has really any particular geometry to it. But that's interesting that he's modeled what these things would look like in each of these with his software. And that kind of gets out what the differences are. Okay, now oops, let's see here. There was a picture of the liquid model drop over there. Where everything is just kind of like there's a surface, there's a volume. He's talking a lot about the liquid drop model in this section here. And how it meets basically the pattern here. We have binding energies here. There's a pairing effect between protons and neutrons. So this is basically an analysis of like the liquid drop. So we have atomic radius data here. I think this is more liquid drop. That was liquid drop he's discussing. Then we have cluster models. In particular, the clusters of alpha particles, which is basically helium nucleuses. And this is the chart we showed before, that anything divisible by 4 seems to be somewhat magical. And there's a chart of molecular structures. Not exactly sure what that's about. So this is all about clustering, or basically alpha model. But there does definitely seem to be something about the number 4 and something about the helium nucleuses being significant. So that is basically like the alpha model. Then we have Pauling spheron model by Linus Pauling. He's trying to account for the shape based on these clusters. That's an interesting picture he's got there. And we have independent particle model. So he says mainstream nuclear theory is the shell model. This is as close as we're going to get to what scientists may agree upon. So this whole section is on the shell structure. And there is a lot of data here. Then we've got other models. Finally, we have lattice models. And they don't have my model and they don't have Bill's model here.
And they don't have a Zhukovsky's model.
And they don't have Zukowski's model here either. So like I said, next week we can concentrate on those. And the challenge is to fit as much of this data onto your model as possible.
I want to start with Eric's model,
At least wave your
alpha
hand.
particle. You know, it's too many of them nowadays. You know, currently. Just look at this.
Too many more. Start with resolving the wave particle paradox.
Yeah.
You want to resolve wave particle duality?
Yeah. Let's try that.
Oh, that's easy. Just get rid of the wave part. Get rid of the wave part. Everything becomes much easier.
No.
Many physicists are in denial like that. The way to do it is to understand the concept of the threshold. There's a subtle difference between thresholding and quantizing.
You have some problem with your mic, I think.
Yeah, there's something with your microphone. We can't hear you.
How about now? Can you hear me?
Yeah, we can hear you now.
Is that better? All right. So
They still,
I don't know what's
now you're
going
cutting out again.
Look, I'll just blabber about wave particle stuff. I'll let you go. I'm sorry. I don't know what's wrong with my computer.
All right, so now the next section is about this problems in nuclear models. So one of this problem is mean free path of nucleons in a nuclei. So I'm not exactly sure what that problem is here. It's something about they can't figure out how far it takes for one of the other nucleons to bump into the other one. So I'm not quite sure why that is such a big problem. But apparently it is. So here's a bunch of quotes saying why it's a problem here.
Okay, it's kind of orbital model, kind of.
Yeah, kind of orbital. There's something about the nuclear pieces can't orbit or something and be consistent with the model.
There must be a wrong model, actually. What is orbiting are particles inside the structure, inside the proton, inside the neutron, you know.
So there's a whole big section on mean free particles. And
This
I don't
particular
really
model,
understand why that's the problem. It goes on and on and on and on and on about that.
So actually,
Weierstrass solution.
all this is about independent particle model, kind of, right?
Yeah, it's all saying, why is this not working? Further doubts. In order to account for single particle orbitals in dense nuclear matter, the Pauling solution must be invoked to preclude the existence of any significant nucleon clustering in the center of the nucleus. So basically, they're saying that if you that basically the main thing that we see, which is all this data clustering around the number 4 and around the Nobel inert gases, can't exist if you think that these models are valid. So there can't be an clustering, which is a big contradiction. So I think that's basically their main point, that you wouldn't be able to see any of the data that we see. So they're saying that the independent particle model demands a very lengthy free mean path, but all the experimental data says it only has about 3 centimeters for most nucleons. So that's a big contradiction for the shell model, which is the mainstream model. Now we get into nuclear size and shape. We have nuclear density, which is all done with these scattering experiments. And here's an interesting chart. So this is showing what the nuclear charge density is for a proton and a neutron on the left here. So for a proton, we see that there's only positive charge, and very close, under like 0.25 centimeter is where the maximum positive nuclear charge is found. Then it kind of jogs down and it goes down to a fairly level slope, and then has another little bit at the end. But now for the neutron, we see that the neutron actually changes sign, that the interior of the neutron is positively charged, but then after you go about a half a centimeter, the outside of the neutron is negatively charged, kind of indicating some kind of composite particle. And I think some people look at this and can see like 3 particles in, say, the proton, But I think that's really kind of stretching it. You know, they're thinking that there's 3 pieces here because it's got 3 kinds of pieces of the curve here. You got the peak, you got steady slope, and then you've got the tail. So it's like, well, there's 3 kinds of things there. There must be 3 kinds of particles, and I think that's pulling it. That's that's really not very good data for that. Or like the neutron has got a positive piece, it's got a negative piece, and basically I only see 2 pieces there, but some people will claim to see 3 in that data. So I don't really see the 3rd piece of data, the 3rd part that would indicate that, or any kind of structure. But that's very interesting that they have this kind of data. And oops, now I went all the way back to the wrong place. Where was I? So nuclear size and shape. Let's get back to where. So there's that chart. Okay, so let's keep on going on here. Another chart here. This is charge density. And so they're showing that we have this big outlier with helium, that the core density is twice of that of any other nucleus. But generally, as you get out in radius for the larger atoms, the charge density is pretty constant, and then it drops off fairly rapidly.
The important thing to notice on this chart is that it's a heavier nuclei, the inner nuclear density drops. And some of them even have a well at the middle, in the middle, where it drops down, not horizontal, but it drops more rapidly. And that is what none of the politically correct theories can predict.
Yeah, there's one for like oxygen. I mean, you can see the ones in carbon and oxygen are very unusual, that they start low, they go to a high, and then they drop back down. The heavier elements like bismuth just go straight across, but their charge density initially overall is lower than, say, carbon, and much lower than helium.
Yeah,
so
and
somehow,
so you'd expect them to be constant and not to change as you make bigger and bigger nuclei.
Yeah, or maybe even, higher. If you've got something where you've got all these nucleons together, you'd figure like the interior would be denser, but it doesn't appear. It appears that the charge density is pretty constant for a large atom until you get to its outside.
Bill, this is Harry. I got a question for you.
Yeah, go ahead.
Do all these models use the point particle assumption?
It kind of I mean, they presume that there are protons and neutrons. So those are particles. Point particles, I'm not quite so sure,
Please
but
don't
definitely.
interrupt, Franklin.
Well, who are you asking the question to?
I asked Bill, I thought.
Oh, okay. Well, Bill, go ahead.
They do it one way or another, but the quantum model, for instance, would have particles coming out of, under the uncertainty principle, they come out and then they disappear, and they form kind of like a sphere around a point particle. And so that sphere is effectively finite size, but they can't handle finite size particles, so they just have that, but they have a point particle. And you have the same problem, of course, with the electron in the atom. They don't take into account the finite size. But then you have other problems, because the electron, besides having a charge, has a spin, which is a magnetic moment, and it has a regular dipole moment. So when you look at those, the only way to have that is to have a finite size current loops. And you can't have a finite size current loop in a point particle. So all the quantum models of the atom are off we know they should be falsified by having a illogical assumption of a point particle. But because logic has been removed from the scientific method, none of the scientific theories of the atom or the nucleus are falsified based on false assumptions. None.
Okay, thank you, Bill.
All right, let's go on and see what other data they have here. They're going on. There's, I think I lost my place again.
Can you hear me laughing at that?
No, I think we missed that. You can laugh again.
Oh. Can you hear me laughing now?
Okay, we heard you laughing there. Okay, so there's the radius graph. We had the nuclear skin. Nuclear size and shape. And this is a section on nuclear force.
So I have found those papers of Eric. So I would suggest for everyone to take those 2 papers and let's discuss about this next time and try to offer the explanation or
Nice.
some inputs.
Thank you.
So here we got some quotes from people who are saying that
I did that experiment maybe 100 times over and over, rebuilt it to make sure I wasn't doing something wrong. It was maybe 6 years of work just splitting the alpha and another 6 years splitting the gamma ray. I don't know which papers you're talking about, but thank you.
so here they're talking about the nuclear force, which some people claim doesn't exist.
Well, there's forces in the nucleus, but they're not strong interaction forces and weak interaction forces. They're electromagnetic.
So we can
I
have
agree with that strongly.
An awful lot of data for something that might not exist. So we got potential.
No, it exists, but the nature of it is kind of not well conceived. It's just slightly modified electromagnetic.
Here you can see the islands of nuclear stability in that chart.
Yeah, is that what the? Well, I think they had. Yeah, let's go back to the islands of nuclear stability. That was. Is this the? This is the island, magic island of stability, right? I think that's that there's a predicted region beyond the known nuclei, that there should be something out here, the magic island.
Right. But you need a theory that can predict the islands we've seen, as well as some we haven't seen yet.
So we've got magic mountain, we've got beta stability, we've got the sea of instability.
So, Bill, how many of these do you have supported by your theory?
My theory predicts all the observed islands of nuclear stability, which no other theory does, and it predicts some more that have not been observed. But no attempt has been made to observe them. So that's the interesting part. If we can get people to do the right type of experiment, they can observe these fairly stable nuclei.
Yeah, we'd have to make a nuclei that's beyond 115 or so.
I'm here.
Then we come to nuclear fission, understanding low energy fission processes that have proved so difficult.
Low energy, right? Low energy.
Basic
So-called
facts of fission.
thermal neutrons, right?
So this is all the fractions that they, so this is the problem that I was talking about earlier, which is that when an element undergoes nuclear fission, this is the distribution of its pieces. And you can see that one of the least common things like plutonium or uranium can decay into is a piece which represents 1/2 of the atom. So this is very unusual. Why is it that the peaks show up at basically roughly like 1/4 of the atom and roughly about 3/4 of the atom? So this is a very difficult problem to explain. Why is it when you split the atom, it doesn't split in half? It splits into these pieces. And why are these pieces the most common? So Bill, I was kind of wondering how your model addresses this problem, that we have this asymmetric fission.
The what happens is the nucleus, when it decays or splits, it comes apart because it's unstable. It's going to make stable parts. So it'll tend to make the bigger parts will tend to be more stable than what you start with, and the most stable parts that don't decay a second time are those that are complete shells of nucleons, and so that's how you can describe this, and it works pretty well. And you can we have charts where we have measured the stability and the binding energy of various nuclear isotopes, about 3,500 of them. And so just using that, you can see, if I were going to split uranium into fission, what paths could I go, and what's the probability of each path? And so you can actually calculate that based on energy, stability, and that sort of thing. And so that's how you see all the decay modes, and you should be able to predict all of the modes from your theory. And
Well, that would be saying that, like in this graph of uranium, that you're saying that there aren't any stable elements at an AMU of 120. But I'm pretty sure that's not true. I mean, there are plenty of elements that are isotopes that would be stable at 120, at least as stable as the peak here, which is at 75 and 140.
Well, this is not a, what do you want to say? If you get a table of nuclear isotopes, it will show you the equation for the decay, each of the decays that we measure. And so you can see that this is a little confusing the way they've plotted it. And so you'd have to look at that paper by Geltenbrot in 1986 to see what it is they're actually plotting there. But normally,
well, that what they're plotting here is, I think, fairly clear. I mean, the vertical scale is the number, is its a frequency of occurrence, and then what's in the horizontal axis is the AMU of the particle that was detected. So, like in this graph, around what's it, about 95 is the peak, and about 140 is the peak. So those are the sizes of the atoms coming off of the decay of uranium. It's like right in the center, which is about 120. There's almost nothing coming off of that fission decay that's at that atomic mass. I mean, almost nothing. It's like that is a minimum. I would think that if it had to do with stability, that we would see like data like we had before, which was, you know, strongly influenced by the Nobel elements. We'd see something like that. But this two-hump distribution is rather difficult to explain. because it doesn't really correspond to any of the other nuclear data that we've seen. I mean, why is it that uranium should split up into these, 95 and 140, almost nothing at 120? And we can explain why, it trails off in the smaller elements, but right dead center, you'd think that that would be the most common thing it could possibly split into. I think this is strongly suggesting that uranium is made out of some piece, which is at 95, and some piece, which is at 140. At least that there's some two pieces in the uranium atom that are like that. And actually, it's not just uranium; it's all the other larger atoms basically do the same thing.
Well,
like
those are the most stable configurations that it could split into.
No, I don't think so. That's definitely not the most stable configurations it could split into.
Well,
I mean,
you'd have
definitely
to-
we
you'd
see
have
that,
to-
but
you'd have to look at the decay modes that are measured, observed, and you would explain. First of all, you need to explain why those are the principal decay modes, and when you do that, you'll see there's based on stability of at least one or two of the major isotopes. Like some of the particles coming out are alpha particles. Well, they're very stable; they don't decay.
yeah, and that would be very small. But we're
But
talking
you see,
about
you're
a
getting
particle that's like 95 AMU, which is pretty big.
See, the number 7 is the number of particles you're getting out.
Yes, that would be correct.
Yeah.
Number of particles, so that we see the peaks.
So you're going to get a number of smaller pieces like alpha particles, or maybe something a little bit bigger coming out. But the probability of getting a big piece that's fairly stable is almost zero, as you can see, because
well, I don't even think these are stable pieces. This is just based on AMU. I'm sure they're getting a lot of pieces which are actually not stable.
That's right.
But have that
anyway,
AMU.
they have a much when you get the bigger pieces, you can't have as many separate particles because you use most of your mass of your nucleus to make the bigger piece with the higher AMU. So,
but the picture is indicating that the most likely thing for uranium to fall apart into is one piece, which is at 95, another piece, which is at 140. That's whatever you think, that's basically what the chart is saying. So that is an interesting thing. So this is like all the other elements, and you see all the other elements, no matter how much what their mass is, they all seem to exhibit this asymmetric distribution. And they're, basically they're all clustering here.
Wait a minute. You said asymmetric distribution?
Well, they're asymmetric in that, they've got.
I don't see any asymmetry. They're symmetric. They're mirror images.
Yes, they're mirror images of each other. But I think that's what they call it.
Symmetry.
That's
symmetry.
Well, the thing is, I think what they mean by asymmetric is that one piece comes off at 35, the other piece comes out at 55. And it's not like a flat curve. I mean, you'd think just naively that if fission was possible, you'd probably see an equal probability of any size particle coming out. But that's definitely, that would be symmetric. But we see instead these two humps. So there's definitely two bumps anytime you've got fission going on. So I think that's probably what they're talking about. That there is definitely not an even distribution. So that is telling us something about the atomic nucleus. It tends to break apart in these two things. And this is what they call it. They call it asymmetric fission. So that's a very interesting piece of data. And as they like this quote here, it says asymmetric mass distributions have proved to be one of the most persistent puzzles in the fission process. Although many suggestions as to the origin of the effect have been offered, no theoretical model has been proposed which has been explored in a complete enough manner or has been sufficiently free of parameter fitting to be generally accepted. And another thing, this is against the liquid drop model. The most significant failure of the liquid drop theory is the failure to account for asymmetric mass distributions. Because you would think that if it's a liquid drop, then the most likely thing would be a piece where it would split it in half. So that the half should be the most common thing. But that turns out to be the least common thing. So this is pretty significant. If you've got a model of the atom, it must clearly explain this.
Plus a lot of other things.
Yeah, but this is a pretty obvious piece of data that you got to explain. You can't ignore. You can't ignore that. Why we get this two-peaked nuclear fission?
The nice thing about this book is it shows you all the irregularities of the various theories. And that's nice to be able to get all that in one place, you know. And so the politically correct books are not allowed to tell you these things. So you won't find it. Like in none of my textbooks, I was a major in nuclear theory, you know, for undergraduate degree, master's, and PhD, and none of my textbooks covered this data.
Yeah, because it's embarrassing, because they could show it to you, but then they couldn't explain it.
That's right. They only
So
they only show you what they can explain.
So this is a major thing that is hard to explain. Why we've got that. It's like, what on earth is this chart showing? Plus, they show you all the data. You know, they're just not showing you one little piece because it's theirs or someone's data. They show the data, the whole data, and you know you can explain. You have to explain like those things, like that nuclear density chart, where you know they only show like one, but they don't show carbon, which is kind of strange. So that is asymmetrical fission, which is interesting. So now there's a section here on low energy nuclear reactions. I think this may be new here, mentioning Fleischmann and Pons. So what is he doing here? So this is about cold fusion, which is what I was talking about last time. And they're talking about excessive heat. But really, these experiments produces so little excessive heat that it's kind of hard to tell what was going on. I mean, even if that was absolutely true, the amount of excessive heat wouldn't have been useful. Then they're talking about nuclear transmutation. And that was regular nuclear fusion by shooting accelerator beams at it. I wonder if they're going to talk about. So this is more about the Pons and Fleischmann experiments with palladium. More about palladium. It's like, I don't care about palladium. I can fuse carbon and oxygen atoms. It's much more exciting. Okay, then we get into his own theory, which is the lattice model. Let's see, what did he have to say about his own model? So FCC lattice, that's what he's talking about here. Principal quantum number. Once again, there's his pictures there. So he's got helium, then oxygen, calcium. Now you see his model here with oxygen. Now we know that oxygen likes to bind together with two other molecules, generally at a 90-degree angle like water, like H2O. But one of my criticisms of these types of models is that you can see that the nucleons are evenly distributed. There really isn't anything that would indicate that where the two hydrogen atoms would bond to the oxygen. And like for calcium, that likes to bind with like one or two atoms in a linear fashion, and it's kind of hard to see how that could be possible with this. You can just generally see that it builds up in shells, which build up on generally an octahedral pattern. So he's got his models here. So let's see, what are the color codings here? You've got yellow and red and purple. I presume those are the protons and neutrons. Well, actually, no, the colors denote the different shells. So there's no distinction between protons and neutrons in this model. Then what exactly is the purpose of the neutrons then? So here he has each of the shells is represented by a different color on the outside. He's got 5 levels of nucleons. Of course, none of this has any relationship to, like, say, the electrons or how those are working, since I believe this particular model does accept the Rutherford model. But let's see, what's this chart? This is, because there's a difference between the shells in the nucleus and shells in the electrons. So shells within the nucleus would go towards stability, but wouldn't say anything about what the shells are for electrons. And then this is a comment on the magic numbers. So the magic numbers are 2, 8, 20, 28, 50, 82, and 126. So we got some more pretty pictures of what this octahedral structure looks like. But at least he has pictures. Typically, there are no pictures of the nucleus because it's so unknown what it is and so randomly oriented that it would be hard to make any such picture of any atom. I think about like the latter third of the book is about that. So lattice gas model, what is that about?
It looks like if you buy the book on Amazon, he also sent you some CDs with software that help you visualize what his ideas.
Yeah, but I think someone already put in the chat box that you can freely download all his stuff right off the internet, off the website. So if you just go to that website, you can download the software that he's used to create all of these pictures here. But he's trying to justify his model by comparing the data against his model. And like I said, that is something that anyone who has a nuclear model probably needs to do. They need to compare this data and try and explain why we're seeing these kind of things. But I think that pretty much does it for Mr. Cook's book here, where he's just explaining his particular model. So how does he explain the fragment sizes? That's an interesting thing.
How did you come to be interested in this book?
Well, I have my own nuclear model, which I call a cubic atomic model. So of course, I'm always searching for things about atomic models, and this just popped right up, and there's a whole book. So that is my interest. So next week, like I said, we can go into the various atomic models, like say my own or Bill's or anybody else's. And Zhukovsky. So if you want to bring some PDFs, some pictures, email them to me, then I can put them on the presentation. We can talk about that.
But would it be also possible for me, for example, to take control of the screen and then?
Yes, it is possible. I can hand you control. You can send me some documents. You can then take control.
But so it's necessary to send to you. I could also.
Yes, it is necessary for you to send it to me.
For my.
No, you have to send it to me so I can load it on the presentation.
Okay.
Does he discuss how the nuclear fission that powers atom bombs was discovered?
No, I don't think so. This book is primarily on the atomic models here. So I don't know that he really explained the asymmetric fission with his model there. But in any case, so there's a lot to read here. I think we're pretty much finished reviewing what he's got in the book here. Clearly, there's a fair amount of data that's been presented. Let me see if I can try and summarize what we saw there. Okay, since we've gotten to the top of the hour. So today we've been looking at Norman Cook's book, and we have the download here, and actually like the software is actually all available. So we start looking at the data that his book had, and I think that's probably the most important resource here is that he's got his data. So, and we have some information that we have to think about, which is that we have to think about that not all isotopes are possible, that there is only certain kinds of isotopes which are possible. So you can't stick an infinite number of neutrons onto a carbon atom. There's only so many you can stick on, or there's only so many you can take away. Another question is, what is the purpose actually of a neutron, and why is it we can't just knock every single neutron out of an atom and have it be stable? I mean, if it's held together by the strong force, then what do you need neutrons for? Another thing that we saw in the data is this, that anything that's basically divisible by 4 seems special. So that we have like these alpha particles and helium nucleuses, and we see lots of data with like the ionization energies that all peak around these Nobel elements, right? There's something special about those things. And then in the book, they do discuss the 2 primary models, which are the liquid drop and the shell model. and they had discussed some problems with these. Most of it being that the liquid drop and shell model can only explain different aspects of the nuclear data, but together can't be compatible with each other. So the shell model says that basically the particles don't strongly interact with each other, but the liquid drop says that all the particles strongly interact with each other. So those are two things which are fundamentally incompatible and together cannot explain all the observable data. The other problem we looked at with the asymmetric vision problem. Asymmetric, yes, asymmetric vision problem. So I would invite you to, if you haven't looked at the book, you can continue looking at it some more. So that gives us some interesting data to try and consider. So at the very least, your theory should, if you have a theory of atoms, it should show why the isotopes exist that they do. You should explain why is it we've got all the data that we saw around and why the number 4 seems so magical in the whole system, and perhaps how the asymmetric vision problem works. So that would be our summary for today's conversation. And like I said, next week, I believe we will probably just go ahead and explore some of the other alternate models as presented by the dissident community. So I'll probably see if I can find some links for the various atomic models that I know about, and I'll share that with the invite next week. But that is what we will do. But that will do it for today's meet. So thank you all for coming, and hope you come again next week.
Thank you. Bye.
Bye.